So today I want to talk about what is, in my opinion, a very interesting topic, and that's probability density. So you see probability density often used to represent, anything from like really the simplest probabilistic phenomenon all the way to like quantum wave functions and things like that. Probability is often used uh, in order to basically create mathematical models of where particles exist, especially in quantum mechanics. It's often used there. So I find probability very interesting. So essentially, how this relates to calculus is you have something called a probability density. So what you have here is an integral that's representing a probability density of 1. And when you see a probability density of 1, that means essentially a 100% chance. So when you see it equal 1, think immediately 100% chance of that thing occurring or whatever it may be. And whatever your boundary conditions are, it could be time, it could be distance, it could be your boundary conditions could be anything, but essentially they go from infinity to negative infinity. And if you're working with a time variable, you're obviously just going to use 0 because there's no such thing as negative time. It all depends on the boundary conditions that you're given for your problem. But yeah, just when you see it equal to 1, think 100%. And if you are ever asked to normalize a function, then that will often mean having some c value within f of x, and you have to solve for that c value by setting your integral equal to 1, and that is how you normalize a function and make sure you have it set from infinity to negative infinity. And now you also have the mean value. This is the equation for how to find a mean value, going from infinity to negative infinity, but instead of just f of x dx, you're taking x times f of x dx, and that's going to get your mean value if you're ever asked for that. Now, you also have to deal with median in probability, which is essentially when you have a 50% chance of something occurring. But your median is not going to be that 50% chance. It's going to be the point essentially somewhere in the middle of your probability function. So it's going to be m, infinity, negative infinity, and there's some point between infinity and negative infinity that is m, and that m is your median. So that's how you essentially solve for the median probability of something occurring. So to demonstrate this, I have an example that I was given in a Calculus 2 exam, which most of this is fairly straightforward, but some of it can actually be a little bit tricky. So we're going to talk about this. I'll read out the problem. So it says, Casey sometimes rides her bicycle into school and other times rides the bus. Let p of x be the probability density function for x, the time in minutes it takes Casey to get to school. The graph of p of x is given below. The area of the shaded region is 0.4. So we have our region here, which is 0.4. And over here, let me move my camera a little bit, we have another region which goes from 30 to 50. And it also goes from a height of 0.1 to the very top of this function. And the very top of this one over here, it goes to 0. Excuse me, that's not. It's 0.04. I thought that was wrong. Yeah, so it goes to a height of 0.04. And that's essentially kind of represents your probability, your y being equal to your p of x, and then the x-axis representing your time variable. So the first question that my exam asks here is explain the meaning of the following integral, and I will write out this integral. So integral from 30 to 50 p of x dx, let's see, in one complete sentence. So what does this mean? If we look back at what we have up here, we can see that we have it between two certain boundary conditions. So this is the amount of time it takes her to ride her bike to school, the probability in essence. So you've got from 15 minutes to 25 minutes roughly. It's kind of in between there. And that's a probability density of 0.4, which is in essence 40%. And then over here, we have it between 30 and 50. So that indicates that the integral p of x from 30 to 50, that's essentially the probability that she will take the bus to school. Because for her to take the bus, it takes between 30 and 50 minutes. So that's what that integral represents. The next problem asks us to solve the integral. And so now this one is actually very straightforward. You can do the math, like take these, calculate the area of the triangles, add it to the area of the rectangle. You can do that, sure, it's fine. But there's a much easier way of doing this. This is a 40% chance. This is a 60% chance. Because basically, we're not given any other kind of option here. There's no option that she's just like not going to go to school or something, or she's not going to take transportation. It's a 40% chance and a 60% chance. And that's pretty much all that, that's all we're given here. So including the rectangle and the two triangles, that's a 60% chance that she will take the bus and a 40% chance that she will take her bike, meaning that this probability density is equal to 0.6. So our next question asks us, when she rides her bicycle, it always takes her significantly less time than when she takes the bus, as can be seen by the graph. What fraction of the days Casey goes to school does she ride her bike in? So this one's very straightforward. We can just solve this honestly via a ratio. So it asks us how many days she takes her bike in. So let's think about this real quick. She takes it in 40% of the time, which is just 40 over 100, which would essentially be equal to 4 over 10 equal to 2/5. So she takes the bus to school, or excuse me, she takes her bike to school 2 out of every 5 days. Because that's exactly what 45% means if you just keep reducing the fraction. So that one's straightforward. Don't need to talk about that very much. The final bit of this is probably the toughest one. What is the median amount of time it takes Casey to get to school? So if you want to try this out, feel free to pause the video, look at all the values we have here and see if you can figure out what the median amount of time is. Okay, so we have our equation up here for the median value of m. So now there's a little bit of a sentence that we can use to explain this. The median value is when half of the area of the integral lies to the right of that point being the median. So half of the area lies to the right of the median. Well, I think we can figure this out. So we have 0.4 and we have 0.6 here. I would be willing to reckon that it might be somewhere around here. So in the middle here we have 40, and this is going to be 35. That's going to be 45. Should have wrote that in earlier, honestly. But let's solve for this region and see what we come up with. So we know the height of our triangle is going to be, well, first we need to write area equals 1/2 base times height. Our height, as we can see over here, is 0.04. So that means that our area equals 0.5 times the area of the base, or times the length of the base, which is 5, times 0.04. And let me just grab a calculator, do that math real quick. So we have 0.5 times 5 times 0.04. And that exactly equals 0.1. So what does this mean? Well, if, say, our median were to be right here, then we would have half of our probability on the left side and half of our probability on the right side, meaning half of the areas on the left and the right, which is exactly what an integral means. So we have half of it on the left and half of it on the right. And that's exactly what this means. So that means that the median amount of time, is going to be 35 minutes. So I hope that makes sense. Definitely be sure to write down these equations here because they are extremely helpful for any probability density problems. And this is one of the examples of a bit more of a conceptual probability density problem. Most are going to involve solving much more difficult integrals. So make sure that your integration skills are on par. But this is just an example of the conceptual ideas. So I hope that you found this helpful.